No, I can't hear you.
Excuse me?
Now I can hear you. Thank you.
Audio is not coming, I think. Excuse me, audio is not coming. Can you check? We are not able to listen.
Yes, sir. What you said?
Yes, sir.
Can't hear the audio. I can hear you.
Given here in this equation, where these PIs are the independent soft terms in the theory. And here the NZ is actually the Z boson mass, which is defined in this equation here. So the issue with these early measures was that they are highly model dependent. And if we follow these kind of measures, one would have some limits on the superparticle masses as given in this table in the second column. So you see that the EWino must be within 400 to 600 GeV if one adheres to this naturalness measure of around 30. And the stock mass should be within 450 GeV and the squark masses should be within 700 GeV. So all in all of these have to be less than a TeV. And this mu parameter that you see here actually controls the masses of the higgsiano-like neutralinos, and they have to be light, around 350 GeVs. But it has been shown subsequently that these measures often ignore correlations between the different soft terms. And in the last 5 years or so, there have been new measures called, even more than 5 years actually. So there have been new measures known as the electroweak naturalness measure, namely defined as delta electroweak here, which is defined as this quantity. So it is basically the measure of the largest term on this right-hand side of this equation over mz squared by 2. And the main takeaway from these kind of measures is that this is defined entirely at the low energy level and not at the high scale level as delta Vg was. So if one uses these kind of measures, it takes into account the correlations, and one sees that the limits on the superpartners from this new measure actually is much larger than what was predicted before. So although the new parameter still has to be light within 350 GeV, the gluinos and the stops can go up to 3 GeV or 6 GeV, and the squarks are even heavier. So one might ask, why is the squark mass limit so much heavier than the stop or the gluinos? That is because the squarks will actually not contribute much to the Higgs mass as compared to that of the stops or the gluinos, mainly because of the low Yukawa couplings there. So if one adheres to this new prescription, one sees that for similar naturalness measures of 30, one can actually have natural SUSY scenarios, which are still allowed by the current constraints, as we will see in the next slides. And one can have a scenario with a light stop as large as 3 TeV, but still be natural. So this is a representative natural spectrum that addresses the hierarchy problem and also provides a higgsiano-like dark matter candidate, which will not actually satisfy the full dark matter, but does satisfy around 10% of the dark matter, as we will see later on. So here, mainly the structure consists of light higgsinos, followed by the wino or the wino-like neutralino and charginos, and followed by the lightest stop and the gluinos. All of this is within a TeV, whereas the heavier first and second generation squarks and the heavier partners of the third generation squarks all are in the multi or tens of TeV regime or higher. And if we come now to the current status from the LHC, we see that in simplified model scenarios, the gluinos are already excluded up to around 2.3 or even 2.4 TeV if one considers a massless LSP. And CMS also presents similar limits close to 2.2 to 2.3 TeV. And one key point here is that these kind of plots are mainly using some specific decay mode. So if you see this red line here, this mainly comes from this decay channel of the gluino going to QQ bar neutralino, assuming 100% branching ratio. So these are the limits which come from this kind of a search. But in a realistic SUSY scenario, one might not have 100% branching into this decay mode, but can have much reduced values. So in such cases, one needs to take into account those branching factors to correctly assess your benchmark scenario or place limits on this. And here, if we compare with our limits from the previous slide, the gluino limits up to naturalness is up to around 6 TeV. So although LHC has really progressed a lot in terms of excluding around 2.4 TeV of gluino masses, one still sees that there is a large parameter space left, which one needs to explore in order to look into the full natural scenario. Similarly, for lighter stop, one can go up to around 1.3 TeV from the current limits for a massless LSP scenario, and similar limits arise from the CMS results. And the electroweakinos, mainly the wino and the wino-like neutralino and charginos here, they also go around up to 1.1 TeV from current searches. Whereas the higgsinos, which we saw before were controlled by this new parameter, they are normally, they are usually very compressed. So there are usually two higgsiano-like neutralinos and a higgsiano-like chargino, and they are normally very compressed with each other in the MSSM. And we see that these searches from MSSM actually still are relatively weak compared to the other electroweakinos, and one can go up to around 150 GeV for a mass difference of 5 GeV. And interestingly, recently LHC, both Atlas and CMS have seen some 2 sigma excesses in soft dilepton and soft trilepton searches, which you can see here. This dotted line is the expected line, and this shaded one is the one from data. So actually, they do see some discrepancies here, and these hopefully will be better answered in the upcoming runs to have a more conclusive statement. So in our work, we mainly look into SUSY from the string landscape. And this was based on mainly motivated from Weinberg's solution to the cosmological constant, where he tried to propose that if one has a multiverse scenario with a large number of possible universes, one can explain that in some of these universes, the cosmological constant might take a small value and do not need any kind of fine-tuning. So following along the same lines, people try to address the origin of the SUSY breaking scale, because as I mentioned before, we don't know how SUSY breaks, but we know it has to break. So that SUSY breaking scale origin, people try to explain in the string landscape scenario. And Douglas et al., basically they proposed a probabilistic view for naturalness, known as stringy naturalness. And their main idea was to sort of look at this scenario in a way that one tries to look at the statistical trends of the different observables like Higgs mass or stock mass over all these different vacua solutions. And suppose we have two observables O1 and O2. The more phenomenological vacua which lead to O2, O2 would be more natural than O1. So in previous work by this group, they have shown that one can actually have low electroweak fine-tuning in SUSY models in the string landscape. And this is mainly seen by a large density of points. So this is one particular model that was considered in this paper, namely where they have two parameter. So this is basically in the NUHM framework where they have two parameters M0 and M half. M0 is the scalar mass at the high scale and M half is the fermionic mass at the high scale. So here, the main point I want to stress is that this green region that you see, that actually fits the Higgs mass constraints from LHC along with the theoretical constraints. So one sees that if one considered the delta BG parameterization before, one would be restricted to such a tiny region of the space, whereas in the stringy naturalness formalism, with this delta electroweak, one can really have a larger parameter space. And this is mostly at large values of M half and M0. So the key point here is that string landscape actually favors large soft terms. So if we consider n equal to 1 scenario, which was also an ansatz put forward by Douglas, mainly they considered a polynomial type of fitting for the SUSY parameters. So for n equal to 1 simple scenario, it was shown that it favors a linear draw towards large soft terms. And keeping this in mind, one also has to ensure that the different pocket universes that you have, they are also phenomenologically allowed. And in order to do that, Agrawal et al., they actually proposed before something called the ABDS window, which is something mainly which checks that the value that we derive for the weak scale in each of these universes, they are within some factor from the measured value, roughly around 2 to 5 times the measured value of the electroweak scale. And this delta electroweak less than 30 actually also respects the ABDS window. And this is the kind of constraint we put on our scenario for the next scans that we will do in order to ensure that we have the correct phenomenology. So since my topic was on anomaly mediated supersymmetry breaking, I'll just briefly go over it. So anomaly mediation refers to mainly these soft SUSY breaking terms being generated from loop contributions, where any tree-level contribution from gravity mediations are sequestered. So in this scenario, earlier Randall and Sundram had shown that one needs to add some extra bulk terms for the scalar masses and the fermionic masses to solve tachyonic problems from leptons. And all in all, they came up with this minimal model which has these free parameters, namely M0, which is the scalar masses, M32 is the gravitino mass, tan beta, and sin mu. And the mass spectrum for this nAMSB scenario mainly is governed by the gravitino mass. And this extra g square by 16 pi square is mainly the loop factor that comes into play. And in this scenario, the winos are the lightest gauginos and the lightest SUSY particle. But there have been very stringent constraints on this model, mainly coming from the fact that one cannot fit naturalness as well as the Higgs mass, and as well as the fact that the Wino dark matter is now very stringently constrained from Fermi-Lab data. So this scenario was next further modified in order to address the Higgs mass as well as the naturalness as well as the dark matter constraints. So what they did was they made some changes to the minimal scenario by taking non-universal Higgs masses, and they accounted for separate bulk masses for the HU and the HV, which are the up-type and the down-type Higgs doublets. And this allowed for a low mu parameter. And in the nAMSB scenario earlier, as I mentioned, that the soft terms are all generated at the loop level. So the trilinear coupling, namely the A parameter, this would be important because this actually also contributes to the mixing in the top sector, in the stop sector. So that has an effect on the Higgs mass. So in order to have a correct Higgs mass, in MSSM, we know that we need radiative corrections. So what they proposed was that there need to be bulk contribution to this trilinear mixing parameter, which would help with the Higgs mass. So this new nAMSB model now has a few extra parameters, namely different scalar masses for the first two generations and the third generation, and a trilinear mixing parameter, and mu, which is the mu parameter, and mass of the pseudoscalar Higgs. So using this enhanced parameter space, we now try to see what kind of Higgs mass and delta EW, namely the naturalness measure, we can see now compared to the nAMSB scenario. So the green lines that you see on this left-handed plot is coming from the minimal scenario, which was the first nAMSB scenario considered. And the blue one is this modified nAMSB scenario. And this red dotted line is basically the limit delta electroweak equals to 30, which will ensure that you have a phenomenological scenario allowed from ABDS constraints, as well as you are within the naturalness limit. So here we see that the nAMSB actually really has very large delta electroweak values above 100, whereas we have some parameter space for this new scenario which lie below the delta electroweak 30 limit. And similarly, on the Higgs mass side, nAMSB actually is still within the allowed Higgs mass, along with its 2 GeV theoretical error, which normally one has to take into account in SUSY because of higher order corrections. But minimal AMSB actually cannot really go very high. It cannot really account for a very high 125 GeV Higgs mass. So given that we now have consistency from both naturalness as well as Higgs mass, we also have this low mu parameter, which leads to the scenario with a higgsiano-like dark matter. So before I move on to the mass spectrum, I'll just briefly show the results we have from scanning over the full parameter space for this model. So we scan over all these different scalar mass parameters, gravitino mass, trilinear mixing, the pseudoscalar Higgs mass, and tan beta in this range for a fixed mu of 250 GeV. And this choice is mainly consistent with the LHC constraint, as well as the fact that we are adhering to a natural spectrum, which should have a light higgsinos. And all the scan limits mainly are chosen such that delta electroweak for all these scenarios is within the ABDS bounds, that is less than 50. So once we perform this scan, we try to again go back to Douglas's probabilistic measure of looking at observables. So we plot the histograms for the Higgs mass. This is the lightest CP even Higgs mass. And we see that for this scenario with n equal to 1 sort of landscape feature, we see that one can actually predict the Higgs mass to be 125 GeV. So in the subsequent plots, there are two lines, the red and the blue ones. So for now, let's focus on the red lines, which are not after imposing any kind of LHC constraints. These are just from the scan. So here we see that there is a possibility that one can predict the 125 GeV Higgs, and it comes out as a prediction from this scenario. And subsequently, if you look at the heavy Higgs masses, say the heavy pseudoscalar masses, they are normally around 2 to 3 GeV, so they are sufficiently heavy. And one can really sort of be in the decoupling limit where the standard model couplings would also be fine with the LHC results. And coming to the other superpartners, the gluinos are within 2 to 5 TeV. And the wino-like neutralino and chargino, they are interestingly within 300 to 700 GeV. So the classic feature of the nAMSB scenario is that the winos are still the lightest electroweakinos, but they are no longer the lightest SUSY particles. So they are safe from the dark matter constraints. But because this mass range is within TeV, we will see later on that one can actually look for these guys at the LHC and have a conclusive statement about this model. And another feature is that the lightest stops that we were talking about before, they are around from 500 GeV to around 2.5 TeV. Of course, there are limits from LHC we must consider. So this dotted line here that you see is the current limit of 1.1 TeV. So we still have a peak in the stop mass distribution around 1.5 to 2 GeV. And the winos are the lightest one, as I mentioned. Now coming to the higgsinos. The higgsinos in our scenario, as in the MSSM, they are compressed. And one has, however, a slightly larger compression than in MSSM, and one can go up to say 10 to around 40 GeV mass difference between these light higgsinos. And here I will not talk about the rest, but I'll just focus on this M012 TeV, which M012, which basically controls the masses of the first and second generation quarks, and these are around 10 to 20 TeV. So these are very, very heavy and not within any collider searches for the current experiments. But this heavy first, second generation actually helps with the SUSY favor problem as well. So from these slides, I just wanted to mainly focus on two things. One, that in this scenario, higgsinos are the lightest SUSY particles. So in this picture, the blue lines, these are namely the three higgsinos that we have in the scenario, two higgsinolite neutralinos, chi1 and chi2, and a higgsinolite chargino. And they are usually quite compressed. And as we saw in the few slides before, that this mass difference is roughly around 10 to 40 GeV. And these might be interesting from the context of the soft dielectron searches where ATLAS and CMS have seen some excesses. So maybe these are also things one should explore more in the upcoming runs. And here the winos are the lightest of the gauginos, but now the next two lightest SUSY particles. And here the green and the yellow line mainly show the wino-like neutralino and chargino. And this blue dotted line here refers to the naturalness limit. So we will be mainly interested in this this kind of a mass region for our subsequent work. So for this scenario, we mainly focus on the production cross sections of the higgsino-like neutralinos as well as the wino-like neutralino and charginos. So and the strong cross sections from say the stops and the gluinos, these are much lower than the higgsino and the winos. And for any collider study, we need to first ask what kind of final states do we expect to see. So in our case, if we're interested in looking for the winos, we look at the different decay modes of the winos, and we find that they mostly decay to vector bosons V or Z or W and the Higgs along with the higgsinos. So if one looks at the signals, possible signals at LHC, one would have two vector bosons in the final state along with a large missing energy. And this large missing energy mainly comes because the higgsinos, they are the lightest of all the SUSY particles. They won't decay any further. And these are, and the higgsino-like neutralino, which is a potential dark matter candidate, they will simply pass through the collider without leaving any kind of energy deposit. And one sort of looks at these scenarios as missing energy, which balances the other visible objects. So all in all, the final states that one can have from this scenario is two vector bosons plus missing energy, a single vector boson along with a Higgs along with missing energy, or di-Higgs and missing energy. And Atlas has actually already looked at these at some of these signals, namely two so boosted diboson plus missing energy with the bosons decaying hadronically. This has been recently studied by Atlas, and they have placed very stringent limits on this wino-higgsinos mass plane. So this feature translates to the parameter space for this model in terms of this shaded gap that we see here. So this essentially is now currently ruled out from Atlas. And previously, when I talked about EWino searches, the limits from EWinos were around 2.3 keV. So this also actually translates to a lower bound on this parameter space. And maybe this would be more clear if we look at the mass spectrum. So here we see that one can actually have a very narrow allowed region from the current constraints from LHC. And in this very narrow allowed region, we really have wino masses within, say, 300 to around 600 GeV, which survive the current constraints. And one can look for these winos at the high luminosity run in different channels, namely the same sign diboson searches, which can lead to same sign dielectron plus missing energy final states. And these are very interesting final states, namely because standard model like backgrounds are extremely rare in these channels. Another one could be opposite sign dielectron as well as trilepton final states. So we looked at some of these signal states. For instance, the trilepton plus MET channel, which comes from this kind of a scenario, and where these chi2s and chi1s are actually, so this chi2 is the wino-like neutralino and charginos. So here, basically what we see is that one can really have a very large significance for this trilepton plus MET channel, up to around even more than 5 sigma, up to around 600 GeV wino masses. And in this signal analysis, we mainly tagged on to some kinematic observables like transverse mass, PT of the lepton, missing energy, to discriminate between signals and background. And for the same sign dielectron scenario as well, we see that there is a large parameter space where one can actually discover this model if it is present at the high luminosity LHC up to around 600 GeV wino masses. And here also one can use some of these kinematic observables to discriminate between signal and backgrounds. And this scenario is mainly for a light mu value of 150 GeV. So what happens if we go for higher mu values, say 250 GeV? So the main thing one must remember here, as we are increasing the mu value, the winos are still at the 300 to 600 GeV range. So we are essentially decreasing the mass gap between these two. So namely the different kinematic observables we were relying on, they might degrade a bit because now the mass gap is reduced. So the PT of the leptons, the lepton momentum, transverse momentum, all of these are significantly could be reduced. So here we see a slight deterioration in the light wino masses, mass regions, because we have lower phase space here. But it picks up sufficiently as one goes to higher masses. And even in this case, one can have at least a 2 sigma excess or more for wino masses greater than 350 GeV. So all in all, there is some hope that if by the end of the high luminosity run, one can actually fully explore or rule out this scenario. And coming to the higsino-like sector, we can actually look for soft opposite sign dielectron signals along with MET. And here as well, we see that one really has almost over the entire range of the higsino masses, from 100 to 250 GeV, one can really go up to more than 5 sigma for this particular channel for light mu scenarios of 150 GeV, and for higher mu also there is this slight deterioration, but one can really have some excess beyond 2 sigma over 150 GeV. 150 G. Okay, sorry, this is the gravitino mass. So this is not exactly the mass plane, but one can have higher significances even for higher mu values. And the other important ingredient of this scenario was the lightest stop, which we saw from the histogram plots is peaking around 1.5 to 2 TeV. So in this scenario, we mainly look at this kind of a heavy stop, 1.5 TeV onwards, and we see that in such a scenario, the stop actually decays to 3 channels, namely bottom chargino, top neutralino 1, and top neutralino 2. And these neutralinos and charginos are the higsino-like ones, which are roughly around this 100 to 250 GeV level. So one has a very large mass gap between the TeV level stops and the light GeV level higgsinos. And this enhanced mass gap actually helps one to look for boosted top scenarios. So in this case, we look at these 3 different final states, namely 2 fat top jets plus missing energy, 1 top jet plus a B quark plus missing energy, as well as 2 boosted B jets and missing energy. And using a combination of these 3 channels, we can actually see that one can sort of put limits on the stop masses. So what we see is that we can have actually around 5 sigma discovery for around 1.7 TeV stop masses. And one can go up to around 2 TeV stop mass if one looks for 95% confidence level limits. And these limits are slightly better than what Atlas has projected. Current Atlas projection on the lightest stop is roughly around 1.45 TeV. And here we can reach slightly higher, mainly because in this scenario, we know that the stops are heavy. So the cuts that we have designed, they tag on to this heavy stop feature, and with higher cuts for the different kinematic observables, which actually improve the significances a lot more. Yeah, here is some of the sample cuts that we placed, namely on the missing energy, the kinematic observables like transverse energy of the jets, as well as the total effective mass. So all of these were mainly used to suppress the TT bar backgrounds as well as other backgrounds. And a key kinematic variable was this MP2, which really helped in discriminating signal and background. So yeah, I'll come to the end of my talk. So mainly we looked at a natural anomaly mediated supersymmetry breaking scenario, which is consistent with naturalness as well as Higgs mass, and also from the dark matter front. And the phenomenology of such model namely differs from the earlier scenarios in that one has light higgsinos as the lightest superparticle and the light dark matter candidate, and the winos are now the next to lightest SUSY particles. And however, this is one of the few SUSY scenarios which is already very stringently constrained currently from LHC, which really rule out a very large fraction of the parameter space. And one has a very narrow window of 300 to 600 GeV stops, which are fully testable within the upcoming high luminosity run. And the main channels of interest would be the same sign or the opposite sign dilepton plus missing energy, along with trilepton plus missing energy channels, as well as the soft dilepton channel, as we saw, which has a very high significance to be observed in the next few runs. And it might also be helpful in addressing the excesses that LHC has been seeing consistently over the last few years. So all in all, this particular model may be either fully discovered or ruled out by the end of high luminosity LHC run. So that is all from my end. Thank you.
So how are we, like, is there a way to get the hierarchy in the masses of the S quarks? So like you said that you have like S top, which is like the lightest, and like naively, so like I've not tried at supersymmetry, but how do I actually get this hierarchy in this model?
Okay, so actually I have the formula that comes from. Yes, so these are, for instance, some of the mass formulas. Basically, in AMSB scenario, the masses, all of the masses, they are mostly proportional to the gravitino mass. And so these are M1, M2, M3. These typically control the gaugino masses. So wino-like, pheno-like, and neutralino-like, and the gluino masses, they are controlled by these 3. And for the stops, for instance, this mu3 squared, this actually goes into the stop mass. So these have these kind of very long relations. So the kind of spectrum I said, it actually follows from this these kind of formulas.
But then you are like making some choices for the G1, G3, like it's not coming out as a derivation of the model. It's more like what the parameters you choose.
Yeah, G1, G2, G3, they are already from, so standard model, we know the gauge couplings. So they are the gauge couplings which go in, they are fixed. But yes, the gravitino mass is free and the M03, so these are all free parameters. So these are our input choices, correct? So if we use these free parameters, so the scan I was mentioning, we are basically scanning over these free parameters M03, M32, and also the A parameter, which I think does not appear here, but when we scan over these parameters, that kind of picture emerges from these formulas.
Okay.
Yes.
So, you seems to have put a constraint on mu, like you chose, right? It's not a constraint, like 250 GeV.
Yes.
So what's the motivation for that? Cannot you have 400 GeV, and then is that a prediction from your Douglas's naturalness?
No, not fully. So it is a prediction from delta electroweak measure. So,
Is the mu range fixed from delta electroweak?
so maybe let me go to that slide.
So when do I see that mu value?
So this mu value corresponds to this delta electroweak less than 30.
Okay,
So
so
it doesn't-
350 GeV is the one. So then you made a comment that HL-LHC would rule out mu up to 250 GeV. So does it mean that this model can survive beyond HL-LHC with mu being higher than 250 GeV?
So yeah, we have a plot also for the reach of mu. Let me go there. Yes, so for instance, this one is, we are looking for the opposite sign dielectron plus missing energy search. And so here actually, we have gone up to say mu 350, and this is the sort of limit that we have. But okay, I don't have the other plot, but yes, this 350 GeV we kept to the delta electroweak less than 30. That is true. So if we say push the delta electroweak up to 50, maybe the mu value will also increase to higher 400 mu. So in a way, yes, we can say up to LHC, we can say up to 5 sigma, we can look for mu equals to 200 GeV. If a higher mu is there, we might still not be able to see it at LHC. But that will be in conflict with naturalness. We want naturalness measure to be small. So.
But even 350 GeV wouldn't be at the HL-LHC with 95%.
Yes, yes. Because these are very soft, so the higgsinos are compressed, so the soft lepton searches are not so advanced. So if we have, I think right now one can go up to 4 GeV muons. So if we go even lower, maybe at 1 GeV or 2 GeV or 0.5 GeV, then we will be able to cover this. Or in displaced searches, like long-lived particle searches, those can actually help. There may be other channels which would be more relevant than this.
If you have any other questions, the speaker. If not, let's thank the speaker again.